welcome to today's recording on differential equations, where we're going to learn some methods of substitution to solve differential equations. And so we're going to have about 3 different types of differential equations that I'm going to show you, and how to solve these differential equations with a substitution method. And mainly it's going to be kind of like a u substitution or v substitution. We're going to substitute in some function of u or y or v, and what we'll do is we'll get the equation to look like, something that we're used to differentiating. Like, we can turn a differential equation that appears not to be a separable equation into a separable equation. Turn differential equation which doesn't appear to be a linear equation to a linear equation, and so on and so forth. So that's what we're going to do today. We're going to look at equations and try to manipulate the equation to make it look like an equation that we know how to differentiate. So below, we're going to describe 3 different kinds of first-order differential equations that are solvable by means of a substitution. And so the first we're going to talk about is a homogeneous equation. Now, the definition of a homogeneous equation is if a function f possesses the property f of t of x, f of tx, ty is equal to t to some alpha, f of xy, for some real number, then f is said to be a homogeneous function of degree alpha. So what that means is, look at example 1. We have f of xa. If we want to check to see if it's homogeneous, it's all going to be every term is going to be of the same degree. That's what it's basically saying. So I'll show you what that looks like. So we have f of tx, ty. So wherever there's an x, we're going to put tx. So tx to the 4th, plus wherever there's a y, we're going to put a ty to the 4th. We're going to get t to the 4th, x to the 4th, plus t to the 4th, y to the 4th. And we can go ahead and pull out that t to the 4th, and then we're going to get x to the 4th plus y to the 4th. And so it looks like t to the 4th times our original function f of xy. And so here you kind of see that it looks like that. So this is a homogeneous equation, so it is homogeneous. I can't write an H. Homogeneous function, and this is of degree 4. All right, we can look at the next one here. Again, that term is 1, so we really can't substitute anything in there. So we would, if we were going to do f of, let me change back to blue, f of tx, ty, you'll see this one real quick. We're going to get 1 plus t squared x squared plus t squared y squared, which is just going to be 1 plus t squared x squared plus y squared, which you can see here is not going to give us back to the original, so this is a non-homogeneous function. Now, let's look at example 3. See if that's homogeneous. All we're going to do is we're going to substitute in x of t, y of t. So f of tx, ty, we're going to get tx times ty squared, which is just tx, t squared, y squared, which is t cubed xy squared, which is t cubed times the function of xy, which again is homogeneous. So this is homogeneous and of degree 3. All right, so once we know that we're dealing with a homogeneous equation, what we're going to try to do is we're going to try to make this homogeneous equation. We can manipulate it first. So if we're given a differential equation that looks like an exact equation, we check it and it's not, or we check it and it is, we can still solve it using a u substitution. So if we are given m of xy dx plus n of xy dy, and that's equal to 0, it is a homogeneous equation if both coefficient functions m and n are homogeneous functions of the same degree. So that means that when we check to see if they're homogeneous or not, I'd check m, see what degree that is. I'd check n, see what degree that is. If they're both of the same degree, then yes, we will say that that is, we'll say that we are dealing with a homogeneous function. All right, so so once we establish that, then we can say that m and n are homogeneous of degree alpha, and then we can also write, so I can write my m and my n. When I pull out that x to the alpha, I'm pulling out the x value. And so when I pull out the x, I'm just going to get the x on the inside of both m and 1. And then for u, I'm going to be able to substitute or find what that u is. And so u is just going to be y over x. And what I can do is I can do the same thing with y. I can pull out my y alpha. And in this case, v will take the place of x because we're going to make v equal to x over y. And then since we're taking out the y's, what's going to go in there is going to be 1. So we can substitute either y equals, and so from here, so from the first one where u equals y over x, we can say, oh, that's just y is equal to ux, or the bottom is going to be x is equal to vy, and that's where this is coming from. So when we do the substitutions, we can go ahead and substitute in for y, and we can substitute in for x, ux or vy, where u and v are our new dependent variables. And after we do some substitution, a homogeneous equation will reduce to a separable first-order differential equation. So let's show what that looks like. So say we are going to deal with the first one, where we're going to take u is equal to y over x. So that means that y is equal to ux. Now, what I want to do for this one is I'm going to go ahead and take the derivative of that, all right? And I'm going to take the derivative of each variable. So I'm going to take the derivative of the whole thing with respect to whatever value that I get. On the left side, I'm going to take the derivative, and it's just going to be dy. On the right-hand side, I'm going to take the derivative of u and x, because they're both going to be variables. And u, I'm just going to keep u and take the derivative of x, which is dx, but this is a product rule because we're dealing with two variables, so this is going to be implicit differentiation, plus take the derivative of, keep x and take the derivative of u, so I have just du. And so now we can do some substitution. So say we're going to stick with this first one, all right? So if we're sticking with the first one, then m and n are going to change. M is just going to be m of 1 u. And then we're replacing m with this part right there. So, and then we'll say dx plus n of 1 u. But instead of saying dy, we have a different y. Our different y is going to be u dx plus x du. And we're going to set that equal to 0. Now, all we're going to do is we're just going to try to make our, what appears to be an exact equation, we're going to make it be a separable equation. And so now I got to figure out how we need to write that. Well, now m Oh no, my Apple Pen is dead right now, so I'm just going to keep talking. So m and n, they're both now functions of u. All right, we still have dx. So we still have x here, but we've gotten rid of pretty much all of our y's from our equation. So that's okay. So now we just have two variables. We have variables of u and we have variables of x. All right, I mean, y is still there because it's inside the u, but when we're looking at it, it appears to just be of u and x. So now what I'm going to do is I'm going to write all my dx's together. I'm going to bring those together. So I'm going to have m of 1 u. I have that dx over there, but then I also have, I'll say dx plus, I'm going to go ahead and multiply that. So it's going to be u n of 1 u dx plus, and then x n of 1 u du, and just set that equal to 0. All right, now I'm going to go ahead and just pull out my dx, and it's going to be m of 1 u plus u of n1 u, all that dx plus x n1 u du equals 0. And now I want to put one term to the right side, so I'm just going to bring that plus x times n1 u du to the right hand side. So I'm going to be left with m of 1 u plus u times n of 1 u dx on the left hand side, and then on the right hand side it's going to be minus x n sub 1, not n sub, but n of 1 u du. Now notice everything on the left hand side, this whole part is all a function of u. This whole part is all a function of u. This part, dx and negative x, they're all, functions of, or values of x. So what I can do is, now this is a separable equation where I'm going to get all my x's on the left hand side. Dx over negative x is equal to n of 1 u divided by m of 1 u plus u of n1 u times du. And now I'm finished. Well, I'm finished with showing that it's a separable equation. So now we show that it's separable. Now it is going to be easier to just kind of stick right here, and we can just differentiate it from this way to solve for the differential equation. We don't have to get everything to one side. We can just stick it to one side and set equal to 0, and then differentiate that way. Well, we got to get the x's and y's, or we got to get the x's and u's on the same side. But if I brought all this over to the left-hand side, then I'd be able to differentiate all of it. And that's how I'm going to do it. So I'm going to treat all these problems. Now, one way to know, okay, should I use x equals vy, or should I use y equals ux? Well, whatever's simpler. If m is simpler than n, you're going to use x equals vy. If n is simpler than m, then you're going to use y is equal to ux. And that's how it works. All right.